Hello, my name is Kouki Nanai from Osaka Prefecture University in Japan. I'd like to talk to you about solving QUBO with GPU Parallel MOPSO. To begin with, I'd like to present the background of this research. First, the Quadratic Unconstrained Binary Optimization Program, QUBO for short, is an NP-hard optimization program. QUBO is represented by this equation. Q is an n by n matrix, and the x vector is an n-dimensional 0 or 1 vector. Second, according to recent research, QUBO can represent many important combinatorial optimization problems. Hence, if we can solve QUBO, we can also solve many other problems. Third, QUBO can be solved by quantum annealing machines, QA machines for short, if we reduce QUBO to the Ising problem. However, current QA machines can solve small problem instances only. Next, I'd like to present the motivation of this research. The motivation is that we should develop new methods to fast solve QUBO on classical, that is non-quantum, computers or devices without waiting for the development of QA machines. We have learned over research that a method proposed to solve single objective optimization problem instances by transforming it into multi-objective optimization problem instances. This method can generally achieve good approximation guarantees for the original problem instances in polynomial expected time. This slide describes the goal of this research. The goal of this research is to propose a novel method to solve QUBO by reducing it into the by-object bound constrained continuous optimization, BBCO for short. QUBO is a single objective optimization problem. The X vector is a vector with elements that are either 0 or 1. In BBCO, the elements of this X vector are real number, and in the range 0 to 1. And sets the F2 function like this. If x sub I is 0 or 1, this equation is 0. And if x sub I is in the range 0 to 1, this equation is always positive over 0. We can reduce QUBO to BBCO by reducing it to the problem finding x vector that minimizes these two object functions, f1 function and f2 function. And to solve BBCO, we use GPU Parallel Multi-Objective Particle Swarm Optimization, MOPSO for short. Let me show you the outline of this presentation. First, I'd like to talk about our GPU Parallel MOPSO method. And I also explain the different definition of an archive. Secondly, I'm going to talk about the proposed method. And I also explain a fast evaluation of cube objective function. Thirdly, I'm going to talk about experimental results. Finally, I'm going to talk about conclusion and future work. This slide describes our GPU parallel MOPSO method. We have previously proposed parallel MOPSO on a GPU based on the CUDA architecture. I'd like to explain the MOPSO procedure. Step 1 is to initialize the positions x sub I vectors and the velocities v sub I vectors of each particle. Step 2 is to compute the objective functions, f1 function and f2 function. Step 3 is to make an archive. This archive is not the same as a common archive. The next slide shows the difference. Step 4 is to select the global best particle. The global best particle is a random selection from the archive. Step 5 is to update the velocities and the positions. Then go to step 2. Repeat this process t times. Step 6 is to construct a Pareto optimal set. This slide describes the definition of common archive. The common archive is a set of the personal-based solutions non-dominated with each other. This figure shows the personal-based solutions of each particle. The orange circle shows the objective space. The light blue particles are non-dominated particles, which are stored in the archive. Next, I'd like to describe the definition of our archive. Our archive is the personal-based solutions non-dominated by the personal-based solution of the first particle, that is, particle 1. This figure shows the personal-based solutions of each particle. The right particle is particle 1 personal-based solutions, P1-based for short. We store in the archive P1-based and light blue particles that are the personal-based solutions non-dominated by P1-based. Implementing the archive in this way facilitates parallelization. This slide describes the proposed method. We propose a novel method to solve QUBO by reducing it into the BBCO. And to solve BBCO, we use GPU Parallel MOPSO. Let me explain again the method to reduce QUBO into BBCO. The x vector is a real number in the range 0 to 1 instead of 0 or 1, and sets the F2 function like this. BBCO solves two object optimization problems of F1 function and F2 function. I'd like to explain the proposed method procedure. We parallelize computation of main particles with M threads in step 2, 3, and 4. And we parallelize computation of M particles in n-dimensional space with M times n threads in step 1 and 5. Step 1 is to initialize the positions and the velocities of each particle. The x sub I vector is a real number in the range 0 to 1. Step 2 is to compute the objective function, F1 function, and F2 function. Step 3 is to make an archive. Step 4 is to select the global best particle. The global best particle is a random selection from the archive. Step 5 is to update the velocities and the positions, and then go to step 2. Repeat this process t times. Step 6 is to construct a Pareto optimal set from the archive on GPU with one thread. Finally, step 7 is to round off x sub ij to 0 or 1, and then return the minimal recalculated value of F1 function on a GPU. Here, I'd like to propose the first evaluation of QUBO objective function. F1 functions can be computed in order m times n squared time. We divide the F1 functions into two parts. Step 1 is matrix product calculation part, and step 2 is inner product calculation part. Divide the computation of F1 functions in each thread into step 1 and step 2. Step 1 can be computed in order m times n squared times. Step 2 can be computed in order m times n times. So the computational complexity is not affected by the dividing operation. First, calculate matrix Y equals matrix Q times matrix X. The matrix X is horizontal concatenation of X vectors. In this calculation, the ith column of matrix Y has the same result as the matrix Q times X sub I vector. We use QUBO to calculate the matrix product. QUBO includes a highly optimized implementation for matrix product provided by NVIDIA. Step 2 is parallel computation of transported x sub I vector times y sub I vector for each particle with m thread. Inner product calculation is order n time. Step 2 can be efficiently computed in a simple CUDA kernel. I'd like to explain the experiments. We compared between GPU and CPU implementation of the proposed method. We used 45 benchmark problems to compare execution time and the relative error. The relative error is defined by its equation. Number of particles were 1024 to 32,768. Number of iterations were 2,500. This slide shows experimental setup. GPU server has NVIDIA Titan V. We use QUBO to calculate matrix product. CPU server has Intel Xeon E3 with 4 physical cores. We use OpenBLAS to calculate matrix product. Problem instances are proposed by Glover and others. This slide shows problem instances setup. Variables are size of matrix Q size. Density is the percentage of non-zeros in matrix Q. I'd like to describe experimental results. This bar chart shows speed-up ratio of our GPU program to the multi-threaded CPU program. Our GPU program runs much faster than our multi-thread CPU programs. The maximum speed-up ratio is about 200 to 2 in problem instance B10. Next, I'd like to describe relative errors of solutions. Roughly speaking, the relative errors tend to decrease with an increase of the number of used particles. For example, in problem instance D7, we can clearly see that the relative errors decrease with an increase of number of used particles. 32 of the 45 problem instances have relative errors at most 2%. However, accuracy for the problem instances families F with 500 variables and part of the problem instance families B are much worse than other problem instances. Thus, we need further improvement of the proposed method. I'd like to describe conclusion and future work. First conclusion, we have presented an efficiently parallelized method to solve QUBO. Second conclusion, we have empirically confirmed that QUBO can be approximately solved fast for many of 45 benchmark problem instances. Lastly, as the future work, we have to improve accuracy of the proposed method for large problem instances with at least 500 variables. And future work, we have to compare the proposed method with other methods. Thank you for listening.